Welcome everybody to today's digital meetup. My name is Johannes Dollinger. I'm today guiding you through the evening. Welcome everybody. Welcome you all today's digital meetup. My name is Johannes Dollinger with language. We have two talks today. One by Professor Dr. Hinrich Schütze on word representations for deep neural networks, teaching deep networks the meaning of words the easy way or the hard way, and by Dr. Owen Rambow on machine comprehension and a white paper by his company Elemental Cognition. Now, a quick introduction of us, but most of you probably already know us. We are students from LMU and TUM. We are passionate about machine learning, and thus we organize these meetups and want to share with you our passion about machine learning and current research. If you're interested in also organizing these talks or have a good idea for such a meetup, you're always free to contact us. Now, here's the schedule for today. I won't be going into more detail about it. It's also in the video description. We will be using Slido again today. The link is also in the video description. So please post your questions there. We are very excited for this evening. You can ask anything, also stuff that is not directly linked to the content, but rather to the positions of the people that are presenting today. But without further ado, I now give it up for Benno, who will be introducing us to Professor Dr. Hinrich Schütze. Benno, you are muted.
Hi everyone, my name is Benno, and I'm excited to introduce our first speaker, Professor Hinrich Schütze. He is currently the director of the Center for Information and Language Processing at LMU since 2013. And before that, he obtained his PhD at Stanford, was a researcher at the University of Stuttgart, and also worked for several Silicon Valley companies. While his main focus of research are word embeddings and how they're used in deep learning, his interests are actually quite broad and can even lead to interdisciplinary work, for example, with cognitive science or psychology. For people learning more about natural language processing and its fundamentals, he's probably best known for his and Chris Manning's standard reference book called Foundations of Statistical Natural Language Processing that is widely used throughout the world. So I'm looking forward to hearing about his latest research today, and will hand over to Professor Schütze now.
Okay, thank you very much, and thank you for inviting me to speak today. So I have to share my screen. Can you see my slides? Can you see the slides?
Yes, perfectly.
Okay, great. Okay. Okay. Yeah, so the title of my talk is Teaching Deep Networks the Meaning of Words, the Easy Way or the Hard Way. And I'm going to ask the question, where is word meaning represented in deep learning networks? And the first part of the talk is more of a theoretical investigation of that question. And then in the second part, we are going to take the lessons of that investigation and apply it to BERT. And then there's a brief outlook at the end. So where is word meaning in deep learning? I will begin with reviewing the basic embedding concepts that we need here: words, characters, and subwords. And in each case, I'm going to ask, where is word meaning represented? The role of ambiguity is important in this, so I will also talk about ambiguity in each case. So let's start with word embeddings. And I assume that all of you or many of you are familiar with word embeddings, but I just want to set up a particular framework to look at these questions, and so please bear with me. So for word embeddings, we have one-hot vectors at the bottom here this is supposed to be a deep learning architecture, and so we have one-hot vectors here. Then we have the embedding matrix, and here's the representation of a sentence in terms of embeddings. And then these are the layers of the deep network, and of course, usually there are more than two. I'm just showing two here, and I'm using this matrix here as a placeholder for all parameters of the first hidden layer. Of course, usually it's more complicated than just one matrix, but that's just to be able to show it on this graph. And then the representation of the sentence that's computed here at the first hidden layer is a function of the embeddings and of the weights of the first hidden layer. And the same for additional layers. And I'm going to use the word weights here to refer to the parameters of the hidden layers. And I'm going to use the word embedding for the embeddings. Of course, the embeddings are weights too, but it's just easier if you have this terminological distinction. It's easier to talk about it. Okay, so where's word meaning represented here? Well, that's easy. Word meaning is represented in the embeddings. And if we have a word that has two different senses, like suit, for example, it has at least two senses, the lawsuit sense and the garment sense, then those two senses are represented in this one embedding. And then in the case of this ambiguity, the network, if it has learned semantics well, will disambiguate the meaning of the ambiguous word, and then at the next hidden layer, or maybe later in the hierarchy, the correct sense will be selected. So in the case of ambiguity, hidden layers select one of the meanings based on context. Now let's look at the same for character embeddings. So we have the same picture. Now we have character one-hot vectors here and character embeddings here. So where's the meaning? Where's word meaning represented here? The word meaning is represented in the weights of the network. I'm talking about A here, but it could also be in higher layers. It can't be represented in the character embeddings, of course, because if you look at the example of the character S, it is part of hundreds and thousands of English words. So a small embedding like this embedding of S cannot capture the meaning of all of these hundreds and thousands of words. So the meaning definitely isn't here. So it is in the weights of the network. And we know that the meaning is represented somewhere because deep neural networks can solve many interesting tasks that rely on word meaning. And in the case of ambiguity, the ambiguous meanings must also be represented in the weights of the network. And in that case, we preserve ambiguity longer. And in this first hidden layer, both senses are still present. But then in a later hidden layer, one of the correct senses can be selected. Okay, so to summarize, where's word meaning in deep learning? For word embeddings, the word meaning is in the embeddings. For character embeddings, the word meaning is in the weights. Why is that? Because the meaning of a sentence is a compositional function of the meanings of its words, whereas the meaning of a word generally is not a compositional function of its characters, and that is the arbitrariness of the sign. I'm referring here to the principle of compositionality. Compositionality means that the meaning of a complex expression is determined by the meanings of its constituent expressions and the rules used to combine them. And in the context of deep learning, rules correspond to regular processes, that is, non-idiosyncratic regularities in how meanings are combined. If you go from words to sentences, that is usually compositional. So here we have an example: John eats apples, Mary builds houses, Kim writes books, and here we have a pseudo-formal representation of the semantics of the sentence. And you can see that as we go from the words to the meaning of the sentence, there's a systematic way we compose the meanings of the words to get the meaning of the sentence. So that is compositionality. And the same here for the second example. In contrast, when we go from characters to words, that's usually not compositional. So if you go from the embedding of S and U and I and T to the embedding of suit, then that's not compositional in the sense that suit is not a regular function of the meaning of S, the meaning of U, the meaning of I, and the meaning of T. So that's partially the answer to this question, why we have this difference, because the meaning of a sentence is usually compositional, the meaning of a word is not. Of course, word sequences can also be non-compositional, and character sequences can be compositional. So here we have a partially compositional character sequence. Usually that's the case of morphology or compounds. German Gartentor or English database. Database is compositionally related to the meaning of data and the meaning of base. So here we have compositionality on the character level. And there are non-compositional word sequences like hot dog. A hot dog has nothing to do with a dog, and so we have non-compositionality here. So a more differentiated statement of what we're finding here is that for word embeddings, word meaning is mostly in the embeddings for compositional word sequences, but partly in the weights for non-compositional word sequences, and for character embeddings, word meaning is in the weights. Now, what about subwords and BPEs and so on? This is the representation in deep learning that's most often used today for representing text, and that is we use subwords. So, for example, hijacking here is not represented as the single word hijacking, but as a sequence of 3 subwords, hijack and ing. And in the case of word, these are word pieces actually, but I'm not going to make a distinction here between subwords, word pieces, and BPEs. So where is word meaning for subword units like hijack and ing? And I will use as my example here the word dashing. In Word, it's represented as 2 word pieces, dash plus ing. It has a meaning handsome, as in cut a dashing figure, and also it is the progressive of the verb to dash, and I'm going to represent that as the composition of the verb to run, that to dash, and the progressive, the meaning of ing. So how does our schema look for subwords? Where's the word meaning here? So these are my symbols here, MH for handsome, MR for run, and MP for progressive. Now the meanings run and progressive are in the embeddings because they are basically like words. And I mean, dash is a word, so the meaning of dash is represented by the embedding. And similarly, ing is a frequent unit in word tokenization in the word pieces, and it almost always, very frequently at least, represents the progressive. So that is easy to learn here in the embedding for ing. And then to get the progressive of dashing, we combine these two in a regular way because the progressive is one of the frequent inflections of English, and so that is a frequent regular rule that is easy to learn. But the meaning of handsome is in the weights because that is a idiosyncratic combination of dash and ing, which is not compositional. So the network has to learn how to combine dash and ing in these special cases, and therefore that knowledge is represented in the weights. And at the next level, we have the ambiguity is still preserved, and then in the case of ambiguity, again, we select one of the correct meanings in context in the upper layers. So to summarize, where's word meaning? For words, it's mostly in the embeddings. For characters, it's in the weights of the network. And for subwords, the word meaning is mostly in the embeddings, but is also in the weights, as our example dashing showed. So word meaning in the embeddings versus the weights, why would we care about this question? Our hypothesis here is that word meaning in the embeddings is easier to learn than in character embeddings or subword embeddings. And there are two reasons for this. One is no interference. If dashing has its own embedding, then that means there are D parameters reserved just for the meaning of dashing. And these D parameters cannot be used for anything else. They are reserved for the meaning of dashing. When composing the subword sequence dash plus ing, the same weights are used for this composition as for all other compositions. And that means we can have interference. So I'm referring to this these parameters here, and I mean these two, but I'm just going to use these as an example. They have to encapsulate the knowledge about how to do the composition of the units. And these compositions can be regular, like compositional operations, like the progressive, but they also have to encapsulate the idiosyncratic combinations. And so we have one set of weights that is responsible for everything, and so we don't have any reserved parameters for particular composition functions. A second reason for why word meaning in the embeddings is easier to learn is that embedding parameters are cheaper than weight parameters. So, for example, the Google News embeddings, that's 10 to the 9th parameters, and that's pretty easy to learn and pretty easy to use in our systems. But if you have character level systems that are trained end to end, they are very difficult to train. And for example, a recent character level NMT system has an order of magnitude fewer parameters than the Google News embeddings because they are really difficult to train. And that is also, I believe, the reason that the GPT models are not character level models, but they are subword models. Because if you wanted to train them at the character level, you would need an order of magnitude more parameters and even more computational resources than they already require. Okay, so that was the theoretical analysis. And now let's apply this to a practical problem, to BERT. So I'm just going to say a few words about BERT because hopefully most of you have already come across it. So BERT is a transformer architecture, which basically means self-attention. It's a language modeling setup, so we're trying to predict words in a text, words from context. The input here is represented as word pieces. So that's basically the same as BPEs and subwords. And the main innovations are a combination of transformer, which is bidirectional. Traditional language models are unidirectional, with a novel training setup, masking, where we are predicting a word in context. And BERT is a very successful model, and now there are many derivatives of it that perform even better, like Roberta. So our question here is, has BERT learned the meaning of words? Good performance on all of these tasks does not imply that it has, because a lot of deep learning makes correct predictions based on correlations, not based on true understanding. So how can we test directly whether BERT has a true understanding of word meaning? And what I'm going to talk about is based on mainly this paper. I also was planning to work to present some of this paper, but I don't have enough time, unfortunately. And so what we're doing here is to determine whether BERT has a true understanding of word meaning is we introduce probing tasks. And these are based on antonyms, hyponyms, co-hyponyms, and spelling correction. And I'm going to introduce those now. So first, antonyms. What we do is we define patterns like this one. W is the opposite of blank. Then for the W, we substitute words from WordNet, for example, new. So now we have new is the opposite of blank. And then from WordNet, we can find what the gold standard is for this antonym relationship for new, and that is old. Old is the correct substitution here. And then we get new is the opposite of old. And so we ask BERT to predict words here, and we get a probability distribution over words for this context. And then BERT predicts the correct word if the most probable word is the same as the gold word. And then BERT gets a point, and otherwise it loses. And I'm going to write this as this, like this. New is the opposite of old, and so this notation means BERT must predict old. And you can see that this tests for an aspect of word understanding, because if you know what the antonym of a word is, then you have some understanding of that word. And so that's what we're testing here. And this was the first pattern. Right, and just to make sure, so what we give to BERT is this string here, where this is a mask or blank. And so here we input new is the opposite of blank. And then the task is for BERT to predict here at the output that the right word to put here is old. These probing tasks are inspired by GPT, which also operates with patterns like these. And we always use a couple of patterns, like the other ones for antonyms are W is not blank, someone who is W is not blank, something that is W is not blank, and W in quotation marks is the opposite of blank in quotation marks. And the quotation marks can make a big difference. That's why we also have patterns that use quotation marks. Okay, that's antonyms. Then hyponyms. Our patterns here are W is a blank, a W is a blank, W in quotes refers to a blank, W is a kind of blank, and a W is a kind of blank. Examples would be basketball is a game. So this is the blank, and BERT has to put in a substitute a hypernym of basketball here. And again, you can see that this is testing for some kind of understanding. If you know what kind of thing something is, then you have some basic understanding of the meaning of the word. The next one is co-hyponyms. Here our patterns are W and blank, W in quotes and blank in quotes. And an example here would be harmonium and sax. So here BERT has to substitute something that is the same kind of thing as what's before the and. And so if it substitutes another musical instrument here, then we can assume that it has understood that harmonium also is a musical instrument. The final probing task is correction. That one is a little different. The patterns here are W in quotes is a misspelling of blank in quotes, and W in quotes, did you mean blank in quotes? And an example here would be simulation is a misspelling of simulation. Here we're testing whether a BERT on the character level can see that a particular misspelling belongs to a particular correctly written word. Okay, and so if you we evaluate this with mean reciprocal rank, I'm not going to talk about precision. And mean reciprocal rank means that we get the probability distribution of words that BERT wants to substitute for a blank. We rank that probability distribution so that the most probable word is first, and then the second most probable word, and so on. And when we look in that list, where is the correct word at which rank? And that rank is then the reciprocal of that is taken, and we take the average of the reciprocals. So here we have a result of 0.541. That is, on average, the reciprocal rank is 0.5. And so that means that corresponds to a rank of 2. So a rank of 2 is pretty good. So BERT doesn't get it completely right in most cases, but the correct word is very close to the top rank, which is good. And you can see for the other two tests, we get similar results. So what we see here, this is broken down into rare words and frequent words. What we see here is that BERT seems to have a pretty good understanding of the meaning of frequent words. These numbers are pretty good. But if we compare that with rare words, then these numbers are much worse. It looks like BERT does not have a good understanding of rare words. So meaning of frequent words learned well by BERT, and meaning of rare words learned poorly by BERT. So BERT learns the meaning of rare words poorly. One reason is that BERT subwords are often a poor representation of the rare word. So here I have an example, ophthalmoscopy. It's broken down into 6 subwords like this, and you can imagine that it's very difficult to compose the correct meaning of ophthalmoscopy from these 6 subwords. It means the art or the instruments you need to operate on the eye, I believe. The second reason is that BERT subwords are sometimes okay, but higher layers have learned the composition function for these subwords poorly. So for example, for the misspelling resign-teon, a misspelling of resignation, the segmentation looks pretty good. I mean, resign is the root of resignation, so you can get to the meaning of resignation from the meaning of resign pretty easily, one would think. But actually, BERT fails to do that in our experiments because it cannot do this composition. That's something that it has not learned from its training set. So how can we solve this problem? And we have a couple of ideas that we combine. The first idea is change as little as possible. The only change we will make is to replace BERT's embeddings of the rare word with a new improved embedding. And this is very important for at least 2 reasons. One is we don't have the computational resources to retrain a BERT model or a Roberta model every time we want to change something. And the second, so we can't actually do it, or many labs or many companies can't do it. And the second reason is that it's also environmentally irresponsible to do that, to do a huge training job, everything you want to change something. So the beauty of our approach is going to be that we don't have to change anything about the trained model. We just change the embedding layer. So for example, we replace ophthalmoscopy, these 6 subwords, with a new embedding of the single unit ophthalmoscopy. And we can run, with this new embedding, we can run BERT in the ordinary way. There's no change. We just make sure that this embedding is used instead of these 6 subword embeddings. Note in particular that the composition weights in the higher layers are not changed. So we are not changing anything about the composition functions. They generally work pretty well, and so we're not changing them. The second idea is that we use both surface form and contexts of the rare word to learn a new embedding. By surface form, I simply mean the character string of the word. So for example, if inaccessible, the meaning of inaccessible has not been learned well by BERT, then we should use accessible as one source of knowledge to be able to infer what inaccessible means. That's pretty obvious, but BERT segmentation of inaccessible is actually this, inaccessible. So you can see that for BERT, it may be very difficult to see the relationship between these 4 subwords and this word, which is tokenized as a single unit. And so that's an example why the character string is something that the surface form is something we definitely want to use to infer the meaning of a word. And of course, contexts are the main way humans usually learn words. If there's a new word and if we encounter it in a couple of contexts, then we usually can guess what the meaning is. There's a third idea that we are using here, and that's actually the key idea, and that's mimicking. We learn a new improved representation for a rare word by training a model to predict existing representations of frequent words. So we train a model to predict, based on surface form and context, representations of frequent words like grammatical, republican, classical. And so this is a model that is separate from BERT. It's a completely different model that is the mimicking model, and that mimicking model has the task of mimicking embeddings based on a representation of the word as a surface form plus context. And so once we have that model, we apply this model to predict, again, based on surface form and context, a new improved representation of rare words like inaccessible. And usually I explain this with my gestures and looking at the audience, and unfortunately I cannot do that right now, so I have to put this in words. But since this is kind of the critical part of the model, I want to say it in more detail. So, I mean, BERT has many words in its vocabulary, and we can just look up the embeddings, BERT's embeddings for these words. So that's going to be our what we want to predict. And then we can, of course, we have access to the surface form of, for example, grammatical, republican, and classical. And then we can also go to a corpus and find context sentences for grammatical, republican, and classical, sentences in which these words are used. So that gives us the basic information, the surface form, and the context. And now we have a separate model that, based on this information, predicts the BERT embedding of, for example, grammatical. And we can train this model to do a good job at doing this prediction. And once we have the model, we can then apply it to the surface form and the context of inaccessible, and the result is a new a BERT embedding for inaccessible, which will be compatible with the embedding space of BERT. So here's the actual model that we use. This here is the surface form part of the representation, and these are just character n-grams. And this is the context part of the representation, and these are representations of the context sentences, the context embeddings. We have a self-attention layer here so that we can find, I would say, clusters in the context. So if there's a cluster of contexts which is where the contexts are all self-similar, then it's more likely that reflects the true meaning of the word as opposed to an outlier. And so that's why we use this self-attention layer. And then we have a gate here that can learn how to weight surface form and context, and depending on the word. So it's a function of the word, and it can apply different weightings for different words. And the output then is the BERT embedding of the word. So that's the V here, and that's, as I said, an embedding that is a natural fit for BERT's embedding space. Okay, so we call this model BERT plus AM, BERT plus attentive mimicking. As I said, we don't make any changes to the BERT model. The only change is that the embedding layer is modified, in the sense that if we have a attentive mimicking embedding for a word, then we use that instead of the original BERT word piece embeddings. And you can see that we get vastly improved performance, at least for antonyms, and also much better performance for hyponyms, co-hyponyms, and also vastly improved for corrections. So that means that now, for example, for antonyms, the performance is almost as good for rare words as it is for frequent words. The gap is larger for the others. But for corrections also, it's, well, for corrections, there are no frequent corrections in our corpora, so it's a little bit difficult to compare that. For frequent words, we don't get, either we get no improvement or it gets even worse if we apply attentive mimicking. And that makes a lot of sense, because frequent words, there are a lot of examples of them in the training corpora, so it's easy for BERT to learn them from the corpora. Okay, so what is the reason for this better performance for rare words compared to BERT, the better performance of BERT plus AM? So the first reason is that we use word representations, not subword representations. And that was the lesson from the first part of the talk. The composition function network weights are no longer needed. So if I have a complex composition, like for ophthalmoscopy, where I have to put 6 subwords together to get the meaning of the words, that is no longer necessary. I have a nice word representation that I have learned with my special model that's good at producing good word embeddings. So one way to express the same thought is that we've gone from a model where a lot of the word meaning is represented in the weights of the model to one where much more knowledge about the word meaning is represented in the embeddings. The second reason why BERT plus AM does better on rare words than BERT is that attentive mimicking taps information for representation learning that BERT does not have access to. The surface form, of course, because that's not available to BERT, and the attention that looks at all contexts of the word at the same time. BERT only sees piecemeal information as it walks through the corpus, but our model sees all of these contexts of the word at the same time, and that's a potentially more powerful representation. Okay, that's the end of my talk already. A quick outlook. So intuitively, each unit seems most appropriate for some cases. Hot dog, I would say, is best represented as a phrase. A bloom is best represented as a word. Blooming is best represented as the 2 subwords bloom plus ing. Simulation is probably best represented as a sequence of characters. BERT plus AM is a partial fix for this, but the larger question is, how can our representations simultaneously capture units of different granularity? And then an intelligent model could select the granularity that is most appropriate for a particular case. And so currently we only use a single granularity plus the character level in some cases. So that is a limitation that we should overcome. That's future work, right? Okay, that is the end of my talk, and I would like to thank the European Research Council for funding this research, and would be very interested in your questions.
Okay, thank you for your talk. It was quite exciting to learn about the different distinctions of granularity. So you can ask your questions now on Slido. I will wait a few, I guess 1 minute, if there are any questions, and otherwise I will have 1 or 2 of my own.
Is the Slido publicly available?
Yes, it's in the YouTube. The link is also public, yes, but I can read the question.
Okay.
So we have the first question. Someone is asking, BERT AM is trained to mimic the BERT embedding and then fine-tuned to get better than BERT. Can you elaborate on what are the labels for this fine-tuning?
So it's not being fine-tuned. So it is basically it's conventional machine learning, supervised machine learning. You have a training set. The training set consists of it consists of the frequent words for which BERT has embeddings, and we assume that those embeddings are high quality. And so that's the output, and then the input is the context sentences and the surface form. So we can build a context, we can build a training set for supervised training using this information, and then we just do ordinary supervised training. So there's no notion of fine-tuning or needing any kind of specialization. There's one detail I omitted, which is the number of frequent words, frequent content words in BERT's vocabulary is actually not very large. And these frequent words are also somewhat untypical for the rare words we're interested in. So there's an important other component that I didn't mention because there was not enough time, and that's what we call one-token approximation. And that allows us to approximate tokens for other words that have that are broken up into several word pieces by BERT. And so we get an additional set of such one-token approximations, and that gives us a training set that's large enough and that's also representative enough for rare words that we get good results.
Okay, thank you. I'm just going. Okay, the next question is regarding GPT. I wonder what the performance of the GPT models on such understanding tasks is in comparison to BERT. Have you done any kind of comparison?
No, unfortunately, we haven't. I mean, the idea of the patterns is that they should be very general. Let me show the patterns again. So it is actually potentially important that the period appears here. And as I said before, it is actually, where do I have a pattern? For example, here, it is actually important to make the distinction between quotation marks often change a pattern dramatically. So it is important to be able to use quotation marks as well. And in general, we want this to be a framework that can accommodate patterns of any kind. And that means we cannot use a left to right model like a GPT for this task. So you would have to change something to be able to accommodate GPT. I'm not sure whether that is the question or whether the question is whether GPT-2 has a good understanding of rare words. And that would be interesting to check. I would be very certain that it, for example, doesn't have a good understanding of ophthalmoscopy, because it will have the same problem that we analyzed in the first part of the talk, that ophthalmoscopy is broken down into a nonsensical sequence of subwords, and so it's very difficult to learn the meaning of such a word, and so I would expect that it doesn't understand words like that.
Okay, thank you. I think the next question also goes into something I wanted to ask myself, and it is, how can we be sure that for the frequent words, for example, BERT actually understood? It might have just seen the filled-in patterns during training. And on a more general, in a more general way, I would also wanted to ask how much we can talk about meaning or understanding it, if it's if it's still just co-occurrence and surface form, sort of.
Right, good question. I mean, if you look at the contrast between the two models, like here, for example, the difference between 0.234 and 0.529, I mean, this cannot be due to having seen the patterns in the training corpus. If it had seen the patterns, then the number here would be good. I mean, what we're adding here is not any additional pre-training corpus. So I think this contrast shows you that most of the effect we're seeing here is not due to pre-training already containing the patterns we're using. But I mean, I definitely agree with what you implied in your question, that this is not a complete test of understanding, of word understanding. And actually, that's some follow-up work we're doing. It is a somewhat limited test. I mean, I think if you know what kind of thing something is, then that is certainly some understanding of word meaning. I mean, it's one important aspect of the meaning of a word, but it's very little. I mean, I'm not sure I can put a number on it, but it's a relatively small percentage of the entire meaning of a word. And so we need tests that are much more complex and differentiated to get at the complete meaning of a word. And that is something we're working on right now. But it's a difficult problem, at least if you want to do that without constructing, without doing a lot of human involvement, if you want to construct these tests automatically, which is what we were able to do with this test set.
Okay, thanks for the answer. There's one more question. How much time do we still have, Johannes, before I go into too much?
We can definitely still take the questions, the last question.
Okay, then that's the last question, I would say. So someone is asking, would you say that your mimicking method is a good way to adapt BERT to a specific domain that has very domain-specific vocabulary, for example? I think that's an interesting question. Yeah.
Yeah, great question. Yeah, I think it's a wonderful method of doing that. And actually, we have done some work on that, which is on arXiv, that uses a slightly different method, but it does exactly that. So it does domain adaptation, for example, for medical text by using the same idea. You don't have to change anything about BERT. You just change the embeddings of technical vocabulary, and you get, for example, for named entity recognition, you get clearly improved results if you do that.
Okay, that sounds pretty cool. I think we're done for now. There are no more questions also, so thanks for the talk. It was quite enlightening for me. And I think we have a small break now, right, Johannes? Yeah. And after that, we will be back with Owen's talk.
Okay, thanks for having me. Bye.
Thank you. Bye.
Bye-bye. Welcome back, everybody. We are now entering into our second talk by Dr. Owen Rambow. I will quickly introduce him to you. So we're very glad to have you, Dr. Rambow. You are a computational linguist having a PhD from the University of Pennsylvania, and then you spend an amount of time researching, working both, for example, at the AT&T Bell Labs, but most of the time at Columbia University as a researcher and teacher. Then 3 years ago, you moved into a company called Elemental Cognition. Now, I won't go into the details, but as you all already know, I'm very interested in artificial general intelligence. And Elemental Cognition is probably one of the companies that has the most advanced systems, AI systems, that we can imagine currently. So we are very excited today to hear about the white paper. What exactly are you doing at Elemental Cognition, and what is your outlook on the future? What are you trying to achieve with your really very sophisticated AI system? So thanks for being here today. We are very glad to have you. The floor is yours.
Thank you very much, Johannes. Hello, everyone, and thank you for inviting me. After that introduction, the bar is set extremely high, so I'm slightly worried here. This talk, in some sense, fits very well with the talk by Hinrich Schütze, because it's an investigation into how do we know what machines actually understand when they claim to understand something, and where is meaning located, and how do we know that there's a representation of meaning in a system. I have changed the title of the talk a little bit to be a bit broader. What is Elemental Cognition? As Johannes already mentioned, it's a small company formed by a group of IBM researchers who created Watson. The group is led by David Ferrucci, and Watson was a system that won against humans on an American TV quiz show called Jeopardy. And this was I believe this was in 2014 or 13 maybe. This was an important event for people doing research in natural language processing because it made cocktail parties easier. Earlier, when you met someone at a cocktail party and they asked you, what do you do? I do research in natural language processing. What is that? But after this Jeopardy event, you could say, did you see that Jeopardy show where a machine beat the humans? That's what I work on. So it sort of crystallized in many people's minds that machines can actually deal with language. The goal of this company now is to create software that can do deep understanding of language. And David Ferrucci is the first to admit that the Watson system does not do deep understanding of language. It just marshals lots of surface patterns to be able to beat humans at this quiz game. This new company of his, however, is aimed at creating deep understanding of language. We are not application driven. There's a core research staff of about 20 of us working on NLP and reasoning. And the corpus we are using for the development purposes consists of children's stories. Now, children's stories are not something that form the basis of a very lucrative application. Of course, there are applications in education, but these are not, unfortunately, very lucrative. And of course, on the side, we are exploring some applications, but that is quite separate from the core activity at this point. So overall, this is a moonshot project in the sense that it has a high risk that it simply fails after investing a lot of money. But if it does not fail, it is likely to have a high payoff in that it will really move ahead the abilities of computers to understand language at the level that we humans do. And just want to mention that the presentation choices here are largely my own and not the company's. I want to talk about three things. The first is what is machine reading comprehension and how do we measure it? That is based on an ACL 2020 paper, the white paper that Johannes mentioned. I then have a few slides about the elemental cognition approach. They are unfortunately fairly superficial, partly for reasons of protecting intellectual property. And then I have some details about natural language generation, which most likely I will skip because I will run out of time, but I'm happy to talk about them if there's interest. And in general, this talk will be far less technical than Hinrich Schütze's talk and sort of more programmatic. Yes, this is a paper that this section is based on. And so we observe that, so the term machine reading comprehension, by the way, I will take as being essentially synonymous with deep understanding of language, or deep understanding of a specific text. The term machine reading comprehension links to a whole bunch of literature using the term machine reading, so we chose that for the paper. But I don't see a big difference between that and the notion of deep understanding. Over the last few years, many benchmarks have been developed for machine reading comprehension. And the question that we are asking is, do they actually measure performance of systems for specific tasks? And specific tasks are difficult tasks like answer questions about a clinical timeline in a medical application, assess compliance with regulations or legal obligations, or in a game type application, read a description of a game world and adjust the character's responses appropriately, or in a human-robot interaction, read a human's directions and guide a robot to find the item requested, and so on. These are all very difficult tasks that currently cannot be simply thrown at some existing language model or neurally trained system and be solved. So in this first section of the talk, there are three subparts: what is missing from the text, how we propose to analyze stories, and how we propose to create a new test, and then a demonstration using one state-of-the-art system that, which is representative of all systems today, that existing systems fall short once we use the test we propose. Okay, what are the problems with the existing machine reading comprehension benchmark data sets? We're going to look at a whole bunch of these benchmark data sets and analyze them by how they were created, what the sourcing method is. The early examples were often created manually for the purpose of creating a corpus for evaluating systems. The earliest one is Trek 8 from the early 2000s. And basically humans were given, here's a story, ask some questions that you think a computer should answer, often with very little guidance. The resulting questions were often artificially easy for computers because humans were given no particular guidance to move away from the easy questions. In response to this observation that these early data sets are often quite easy and, for instance, can be solved by very simple pattern matching, the designers of data sets added what we call tricky twists. For instance, they would give the people writing questions not the original text, but a text which contains paraphrases. And this meant that the humans writing the questions couldn't simply base their questions on the words used in the original text because they didn't have access to the original text, and the systems would have to do more complex natural language processing. So that's a good idea, but it led to the opposite problem. Maybe the focus moved away towards difficult problems because that's because the designers of these data sets were adding these tricky twists to create difficulties. So this was testing particular difficult problems, but it wasn't testing a broad understanding of content, of the contents of these texts. A different approach is to use naturally occurring questions, for example, questions users ask in user forums or other online venues. For example, how do I get the first element of a list in Java or something like that? This is basically a great approach because naturally occurring anything is always better because it's already getting closer to what humans do. But it doesn't have the problem of either being artificially easy or necessarily focusing on difficulty rather than content. But it has a third problem, which is it omits obvious questions. What does this mean? That for humans, certain things are obvious, and we also know that for other humans this is obvious, and we just never talk about it. But at the same time, we also know that machines, for them, nothing is obvious. So in order to understand deep understanding, we need to also ask the obvious questions. So an example of an obvious question is if Charles is the father of Mary, then Mary is a daughter of Charles, for example. Not a question we would ask necessarily if the first fact is established, but we may need to ask a computer to make sure that the computer understood. There's a second problem with this, is that we are interested in a model where we have a passage and we go and ask questions about it to see if the computer understood the passage. But in these naturally occurring questions, the passage doesn't come first, the question comes first. And then if a system wants to answer it, there's an information retrieval aspect that comes to find the right passage post hoc. So that's not quite what we're interested in. That's a secondary problem. Then there's another variant of tests that exist independently, question sets that exist independently, and these are tests that are designed for humans, so trivia questions and questions for students. They actually have the same problem as the naturally occurring questions, that they omit the obvious questions. In a testing situation, you're not going to ask a question that you expect a human to know already. There may also be a retrospective passage selection. And of course, we avoid the problem of the questions being artificially easy because they're specifically designed to be difficult for humans, so we don't have that problem. The last broad approach uses algorithms to take a text and to extract questions from that text algorithmically. Here, the problem is that the algorithms are built by hand and they will focus on certain things, and what they typically focus on is difficult things rather than broad content again. So this approach has the same problem as a manually written questions and plus the tricky twists. And of course, we do want to mention in passing that there are some, though not many, collections that do avoid most of these problems. So what our proposal will be is to establish what content system will needs to grasp, and then to check for that content. And by content, by the way, we don't just mean the information that is explicitly expressed in a text, but also the information that is implied by the text or that is relied on by the passage to be comprehensible. And because humans do this filling in, interpolating, adding information all the time, and the goal is to see whether systems can understand text like humans. Okay, now moving on into more details, what we propose as a way of testing machine reading comprehension. And we call that the template of understanding approach. So the basic idea is to characterize application needs and then select passages and then determine the relative passage content and then design the tests. And so the main difference is that we start from asking what our application needs. And the second main difference is how we then determine the relevant passage content. So let me talk about these two steps in a bit more detail. Here, what we do is we look at a whole bunch of text genres and questions we can ask. So this diagram here is supposed to mean the following. These bases here are the genres, and the forms on top are the information that the application needs to extract, the types of information. And what we propose, instead of actually saying our application will be the medical domain or something, we're going to characterize this cross product of genre of text and applications needed to be extracted. And for this particular cross product of a genre and a type of information that an application needs to extract from that genre, we're going to develop what we call a template of understanding that is tailored to these two things, genre and relevant content. And how will we do that? Well, first of all, as genre, we're going to choose stories, meaning narratives, things where a sequence of events happen, where states change, and that the sequences of events and state changes together form something of interest to humans for various reasons. Stories are good as a genre because they're useful for many applications in many domains, medical, legal, business applications, spying type applications, and general interactions online. And the reason why stories are so useful in so many applications is that it is a standard way for us humans to communicate facts. We don't just relay isolated facts. We tell a whole story. I was skiing downhill. I suddenly saw someone coming from the left. I tried to turn sharply, and then I fell, and then suddenly my left wrist started hurting, and blah, blah, blah. That is a story in a medical application. The second reason that stories are very appealing for an initial study is that there's strong evidence for what content applications that want stories, that are processing stories, what those applications will need. And this evidence comes from cognitive science. There was a sequence of research that started in the late 80s on how humans understand narratives. And what researchers found is that there's a small set of things that humans focus on, and that humans can, after they hear the narrative, typically retain for some time and retell, even if the words of the narrative have been completely forgotten. And these are locations, timeline, causes, and motivations. And let me talk about those in more detail. So the idea of the template of understanding for stories is that we take these 4 dimensions that have been identified in the literature and derive clusters of questions for these 4 dimensions. So for spatial, the questions will revolve around where are the entities that are mentioned in the story or that are implied by the story, where are they positioned, and how are they oriented throughout the story. The locations will change, so this is also time dependent. The temporal dimension focuses on the events and states. What events happen when, what is their timing with respect to each other. The causal then also is interested in the relation between events and states, but asks the question, what are the causation relations, which of course interact with the time relations to some extent. What causes what? And by causation, we mean mechanistically leading to, meaning sort of in a physical sense, say a tree falls on a car, the car is broken. Motivational is closely related to causal, but it involves cognitive agents. And so we ask, how do agents' beliefs, desires, goals, and emotions lead to their actions? And it's important to note that this is, of course, a complex area. It's not that simply a desire leads to an action, rather a desire leads to a goal. And given a goal, given the beliefs, the agent forms a plan, and then an action might be part of a plan. So the motivational dimension is quite complex. So here are some, so then the idea is that given this template of understanding, which lays out at an abstract level what types of questions we should ask, the idea is, our proposal is that given a particular text or passage, we create a record of understanding which instantiates a template of understanding for this particular story. So here's an example. The sample story fragment is, one day it was raining when Allie arrived. Rover ran out the door. He barked when he felt the rain. He ran right back inside. Not a terribly exciting story, but one that already poses considerable difficulties for contemporary machine reading systems. So the types of questions in the spatial dimension are, the types of answers in the spatial dimension are, Rover is in the yard from when he runs out the door until he runs inside. And then Rover is in the house from when he runs inside until the end of the story. Temporal things are, Allie arrives just before Rover runs outside, and it is still raining at the end of the story. So you notice here there's some knowledge being applied about how narratives work, namely, rain is mentioned. If the story doesn't mention that the rain stops, and if there's no other reason to believe it stops, we have to conclude it's still raining at the end of the story. Now, moving on to motivational, this, as I said, gets a bit more complex. And here's the question is, why does Rover run inside? Rover, even though he's a dog, counts as a cognitive agent. And the way we do it is we contrast the actions with alternative actions that the agent could have taken. So Roger runs inside rather than staying outside, because if he runs inside, he will be inside, whereas if he does not run inside, he will be outside. And then the because there was a ... here means we actually break that down further, namely that if someone engages in emotion, then that changes their location. And if they don't engage in emotion, it doesn't change their location. And then the next step is if Rover is inside, he will not get rained on, whereas if he is outside, he will get rained on because it is raining. And when it is raining, things that are not covered get wet. And then the last point, the important one that brings these two strands together is that Rover would prefer not getting rained on to getting rained on. And there's another because here, and presumably that will be filled in by general world knowledge about dogs, that dogs don't like getting rained on. So this here represents a whole set of facts we need to know to answer the question, why did Rover run inside? We might simply summarize it to Rover ran inside in order not to get wet, or because he doesn't like getting wet, or something like that. And we might learn that from a large corpus, but that doesn't mean we've really understood why he runs inside. And we're trying to break that out by having this very detailed analysis of the motivation. And our claim is only if a system can answer the question, why does Rover run inside, at this level of detail, has it really demonstrated that it has understood the text at the level humans do. Now, the next question is, how would we actually use a record of understanding in an evaluation? So a record of understanding is a bunch of texts of this form that lay out answers to questions that the system has to answer. So in our internal use at Elemental Cognition, our system produces a specific knowledge representation, which we also use to encode records of understanding, so we can just do a direct evaluation, recall precision. But that is actually not at all what we're proposing for a cross-system evaluation, because we do not want to impose a specific knowledge representation scheme. And in fact, we want to be able to evaluate systems that do not use any knowledge representation scheme, the text-to-text systems, for example. So instead, what we will do is we will have systems produce these kind of answers here that look like the records of understanding. And then we will compare the system output to the questions to the gold standard record of understanding. And there are different ways we can do that. We can either have human judges do that, who can be trained judges, or we can use crowdsourcing, Mechanical Turk. And we can, by the way, augment the record of understanding approach by having a pyramid scheme where several ROUs are created. And this might be necessary if it turns out that different judges come up with different ROUs. So then by having several judges do it and assemble the ROUs in a pyramid scheme, we can perform an evaluation across the different gold ROUs. And then we can also use, of course, technology to automate evaluation. This will be important for being able to develop systems on a quick turnaround cycle. There are simple measures, such as those related to blue. There are more complex ones using semantic parsing, for example. And I just want to point out that this issue of how to do this evaluation is very similar to evaluation for other NLP problems, notably machine translation and summarization. And in fact, this pyramid methods that I mentioned came out of the summarization evaluation and the problems encountered there. So there's nothing sort of special about this. Once we have ROUs, the cross-system evaluation can proceed. It's not simple because we're evaluating text against text, but in NLP, we have extensive experience in how to evaluate text against text. And even though the simple techniques such as blue are only inadequate stand-ins for human judges, we have nonetheless seen that the blue scores have enabled a really excellent development of machine translation technology over time. Now let me get to the last part of this first section and talk about evaluation of a state-of-the-art system on our proposed evaluation. We're going to be using the race stories that were published in 2017. These are English exams for middle and high school Chinese students, so Chinese native language students. They are text and multiple choice questions. In the 2017 paper, the authors reported their best system performance as being 44% against 95% for humans. So it's a non-trivial test set. And we're going to use the first two stories from the dev set. We are not actually retraining anything. We're just using two stories from the dev set. And here is where race showed up on my earlier table. It is, of course, a test designed for humans. And the main problem is that it omits the obvious questions. But we will put obvious questions back in now. So we created a small multiple choice data set based on our template of understanding. So we took these two race stories. We created records of understanding, which, as I just said, are answers to the template of understanding questions: spatial, temporal, causal, motivational. Then we took this record of understanding and turned it into a multiple choice format, because that is how the race data set works. So we ended up with something that looks a lot like the race data set, and can therefore be used by systems that are trained on the race data set. There's one more. We ended up with 201 questions, and we grouped them into 91 variant groups. What are variant groups? A variant group is the same question but formulated very differently. It's more than what is just normally considered a paraphrase. Rather, these are questions that are getting at the same content in the correct answer. Of course, the distractor answers can be different from one another in answers within the same variant group. In question answer pairs in the same variant group. So if you look over here, these are two questions in the same variant group. What actually happened when Mr. Green and the man drove together, and how did the man's direction actually turn out? So in the story, Mr. Green and the man are driving together, and the man gave directions. So asking these two questions is actually asking the same thing. What happened? Where did they end up? And the answer A here, they came to the small house. They came to the small house, has the same content as the correct answer A down here. The directions the man gave led to where Mr. Green wanted to go, because in the story context, it's clear that the small house is where Mr. Green wanted to go. So it's the same content we're getting to, but formulated very differently with respect to the story. And the distractor questions, B, C, D, do not necessarily map to each other. And the reason why we're investing in these variant groups is the following idea, that if you understand this part of the story that the questions are about, then you should be able to answer all the questions in the variant group, because you have this deep level of understanding and you're not distracted by the form in which the question is being asked. The system we use is XLNet from Yang et al. 2019. It's a transformer-based language model. Hinrich Schütze also just mentioned it in passing. It is appealing because it's trained on the books corpus and English Wikipedia, so it has a lot of narrative content, which is exactly what's needed to deal with the kind of texts that are found in the race corpus. And it was trained on the race task specifically, and it performed an 82% accuracy in 2019. Notice it's way up from 44%, showing that both the progress in our field and perhaps the fact that once there's a data set out there, researchers try to optimize their system for that data set. And since the publication of the XLNet paper last year, the best result has gone up a further 5 percentage points. What are our results? So here we show chance, XLNet, and human. We first, let's look at all questions. Chance is simply, obviously, the random guess. It's 15% because the number of distractor questions is between 5 and 6. Humans perform nearly perfectly on it. XLNet, not so much. It performs much better than chance. It has clearly learned something that's relevant to our questions, but it can't answer them fully. It doesn't have the full deep understanding. And when we break it up into spatial and temporal questions versus causal and motivational, perhaps somewhat surprisingly, it does worse at spatial and temporal, as do the humans, by the way. And now we look at the accuracy per variant group. This means we require that if we look at variance groups and say, does the system or does the human answer all questions in the variant groups correctly? Because after all, remember, they're asking for the same content, so we expect the answer to be yes. And we see that the humans perform just slightly worse than on the accuracy per question. The humans get the variant groups. The chance goes, of course, way down, because in chance you get a multiplicative effect. ExcelNet goes down by between 50 and 60% across the board. So again, it's doing better than chance. The decrease in performance is better than chance, but it has not demonstrated deep understanding because it does not typically get all answers in a variant group. So we've demonstrated that, and we take ExcelNet to be representative of today's systems because other systems don't do anything profoundly differently than ExcelNet. The differences are more at the level of details. That current systems do not demonstrate deep understanding of text using our proposed evaluation metric based on templates of understandings. And to sort of wind up this section here, MRC tests, machine reading comprehension tests, should be grounded in the content applications that applications need, and we have chosen the content expressed in stories. It should be constructed from the passage directly in a principled way. That's what our template of understandings are. There are guidelines how to extract a record of understanding, which is what the test should be based on. And it should be comprehensive, including the obvious questions, and those are, as you could see, present in our record of understandings. And this is just the start of an ongoing research program for evaluating deep story understanding or deep text understanding. We have to refine the template of understanding, which we are in the process of doing. We need to build a much larger corpus of story records of understanding, which we intend to make public. We're in the process of doing that as well. We need to develop automatic scorers to, even if they're imperfect with respect to human scoring, but this will allow other researchers to use our approach. And then we can develop templates of understanding for other genres. Okay, I think I'm already sort of at the end of my talk. I do want to show some slides on what our approach is. As I mentioned, I'm not going to go into detail for intellectual property reasons anyway. So the elements of our approach are knowledge representation, NLP, reasoning, and an interface. So the knowledge representation consists of a core theory that just contains the basic elements of logic and such, a large lexical semantic ontology, which is based on two existing lexicographic resources, namely FrameNet and Oxford's NOAD, and world knowledge, which we acquire from web text automatically, which we acquire from crowdsourcing, and then generalize using neural models, and which we can also acquire through the interface from Clara users directly. The natural language processing takes language into or from the knowledge representation, meaning its understanding, for which we use neural models, and its generation, which I was going to go into detail. And the reasoning is an inference engine which uses at its core a symbolic engine, but then neural information to guide the reasoning and to limit search spaces. And then there's an interface which allows direct dialogue with the user, and I'll show some screenshots. Now, those of you who've been around a bit longer or who have done some reading beyond the last few years might wonder now, are we going back to the 80s? Doesn't this sound a lot like research done in the 80s? And the answer actually is yes, in some sense. And the sense is that in the 80s, people were asking exactly the same questions we're asking now. Given a story, how can we get a machine to understand it in the way similar to the way humans understand the story? People were extremely ambitious in the 80s and started with this extremely ambitious goal. And of course, they completely failed. So things are very different now, which is why I think this is a good time to take up that kind of research agenda again. For example, these lexical semantic resources we are using have really only been developed since 2000 and have become available at this scale more recently. Web text, the web didn't exist in the 80s. 2001 is a date that Wikipedia came into being. And of course, it's really grown into its huge size only recently. Crowdsourcing didn't exist. Amazon Mechanical Turk was started in 2005. Acquiring world knowledge from web text wasn't possible in the 80s because there was no web. But even had there been lots of machine-readable text, it would still have been impossible because the technology to extract knowledge from text just wasn't there. And thanks to deep learning, this has finally gotten to a state where we can actually automatically acquire lots of knowledge. And of course, there'll be a distribution over it, and some will be wrong, but it can actually be used. And understanding, natural language understanding, going from free text directly into the knowledge representation of the types that a human would create, a human expert would create by hand, has also now become possible. For example, we have trained a parser using the T5 transformer to parse into our knowledge representation, and it performs extremely well, outperforming by far any FrameNet parsers that were created as recently as 2-3 years ago. So here we are completely profiting from the recent changes in technology, and therefore we can make progress in a way that the researchers in the 80s didn't. Here is the ECX interface to Clara. Clara is the name of our system. Top left is a story. This is a particularly trivial story. Bobby felt warm. He took off his jacket. And the display, it's a little hard to read. The interface people are still optimizing this. Shows the intended meaning. Body as a person, felt as a feeling. It isn't terribly interesting, but when you click on this, you see more information about the word sense attributed. Certainly, generic adjective is not very interesting, but when you click on it, you see exactly which sense of warm is chosen. And then we also get semantic role labeling information. So Bobby is the agent of the feeling, and he is the agent, the wearer of the undressing action, and so on. So that is just communicating to the user the basic natural language understanding that has happened. Here's a display of the entities that the system has found, entities in an abstract sense. There's a single agent, Bobby. There are two objects, the jacket that is mentioned in the text, and the body part from which Bobby takes the jacket off, which is not mentioned in the text, but which plays a role in the reasoning, so we display it here. So this is an example of the kind of implicit knowledge that we feel like we need to test systems on, that if you take off an item of clothing, there is a body part involved. Then there are events. Bobby feels warm, and Bobby takes a jacket off, mentioned in the text, but Bobby cools down is not mentioned in the text. Again, this is inferred. Then we have different tabs here that correspond to the location, which we display as a map, the timeline, the cause and effect, and the motivation. So those are the 4 dimensions of our template of understanding. And just to show the timeline, here we show the events, and we decide that the taking off the jacket and the cooling down happened at the same time. Perhaps not exactly right. And then here are different states that are shown with respect to the events. So Bobby wants his temperature to be medium, is true throughout. It's not great NLG, by the way. I apologize for that. And the temperature of Bobby is high is true until he takes the jacket off and cools down. This here, it didn't quite display, but when you hover over it in the live system, it tells you the body part from which Bobby takes off the jacket is inside the jacket. So before he takes off the jacket, that body part is inside the jacket. And then afterwards, the body part from which Bobby takes the jacket off, the body part down here, the body part from which Bobby takes the jacket off is outside the jacket. And then there's some reasoning that happens that because of this fact, the temperature of Bobby is medium. And that's in fact the conclusion. And note that there's this conclusion here too. The body part from which Bobby takes the jacket off is part of him. It's of course true, but it doesn't start with the taking off of the jacket. So that is in fact an error. This should be true throughout the whole story. If we then move to motivations, we have a different type of representation. Here at the bottom in the white, it's about, first of all, determining Bobby's goal. Bobby feels warm. Then we use world knowledge. If someone feels warm, they want their temperature to go down. So Bobby wants his temperature to be medium. This is a goal. Up here then is a sequence is basically a plan. Bobby takes his jacket off, has a result that Bobby cools down, which means that the temperature of Bobby is medium. Since this result here is, in fact, matches his goal, this means that this sequence of actions up here is a plausible plan to achieve his goal, and therefore we have a possible motivation because one of these actions is, in fact, an action mentioned in the story. So we interpret this action as being part of a goal, part of a plan to achieve a goal which we have attributed to Bobby based on world knowledge. And the final formulation of the answer is Bobby takes the jacket off because he wants the temperature to be medium. And I think I will stop there and skip the details about NLG, and I'm ready for some questions.
Thank you so much for your presentation. You already heard it, guys. Slido is the same link again. Please pose your questions. I will start off with one of my own. I have quite a long list, but I'll keep those to myself for later. Do you have any performance metrics of your system of Clara on the MRC datasets or with your Newto or OU dataset?
Yeah, we are not releasing those numbers yet, but the plan is obviously to do that. The paper that I talked about was part of a track at ACL about where should NLP be going. So it was written somewhat in that spirit of suggesting this new evaluation. And we will be then actually doing the evaluation on our own stories and publishing about that. And again, there's always this is the problem working for a company. It's always a little unclear how much we actually want to publish and how much we only publish after we've solved the whole problem.
Yeah.
So sorry, that's unsatisfactory answer. It's the obvious question to ask. Yes, I agree.
I cut quite a lot of my questions about the system because I believe I would just get a trademark answer, which is obviously very legitimate.
It's
so there's a question. Huh?
It is frustrating, though. Yeah.
But understandable. Quick side question on this issue. How would one go about doing an internship at Elemental Cognition, possibly for the people here, if a person got interested in maybe seeing a detail?
Yes, if you're interested in internship, email me. I have a little message at the end of the NLG section here. So there might be internships at Elemental Cognition, and I will actually be at Stony Brook University starting January 1st. So if you're interested in a PhD, a studentship, or a postdoc, you can also email me for that. So
nice.
Here is my email address.
So we actually have a question by Benno. Do you or Elemental Cognition see a need for grounded language, and in brackets visions agents acting in a simulated or real environment or social environments?
Yes, that's a very good question. We've sort of been finessing that, as one of my colleagues pointed out just yesterday. For some of these things, a jacket, it's important that a jacket covers a torso, and therefore when he takes it off, he will really change temperature. So it matters what a jacket is. But we have some other stories where, for instance, a girl buys a cherry pitter for her grandmother, so a little instrument that takes the cherry pit out of cherries. Actually, nothing in the story hinges on this. There's no mention of how it's used. The grandma doesn't make cherry pie. It is just, the important thing is just that it is a gift. And for those stories, actually, it doesn't really matter that we understand it's a cherry pitter. However, if we did want to generate a picture, it would be extremely important that we understand that it's a cherry pitter and that we can ground this, whatever our KR is for the meaning of cherry pitter, that we can relate that to a picture, and that will be a form of grounding. So At Columbia, I worked on a project called Word's Eye, which is related to this one in that it went from text to pictures and demonstrated understanding by generating a picture. Now, of course, in the case of generating a picture, you have to understand what a cherry pitter is, and how, for instance, someone would hold a cherry pitter, because you want to generate a picture where someone is holding it, and it has to be held in the way that cherry pitters would be held, and not the way in which a lawnmower would be held. So that is totally irrelevant to us. On the other hand, all these motivational questions are irrelevant to generating pictures. So depending on what your goal is, you will have to deal with different questions. And I think this grounding that was mentioned will be absolutely crucial with any application that relates to pictures or video, either interpreting or generating back to. We will need data that links language, either the strings or the KR or whatever it is, to the alternate representation, visual or whatever. However, if we do not have any application related to multimedia, but it's just all language, and if we're testing our understanding using our template of understanding, we do think it's possible not to have grounding in the sense of relating our symbols to a completely different domain of representation, such as vision. That does seem to be possible for the time being.
Very interesting. So we are a little over the time, but I would still have one last question. One of the major parts of your system once was using no deep learning and being purely symbolical, so explainability was one of the core issues you wanted to provide. Does this still hold in your new version with a lot of machine learning?
Yes, because you see, what we see as a major difference between our approach and the approach of, for instance, the XLNet system that tries to learn answers to multiple choice questions is those are end-to-end systems. If once we release a whole set of ROUs that records of understanding, perhaps in a multiple choice format, like the ones in the test case state-of-the-art evaluation that I showed you earlier, then some people might just start training on that, or fine-tuning an existing system using that data, and might get fairly good results. But our ROUs will always require a very, very detailed answer. So those multiple choice questions, that's just the tip of the iceberg. Remember that our ROUs look like, not like these multiple choice, but they look like this, right? This whole thing is the answer to the motivational question. And this is essentially an explanation of the reasoning. If someone can train an end-to-end system and produce this from the kind of data that we will release, which is basically, data of this form, then that's great, good for them. We don't think that will be possible, and that is why we have the explicit reasoning component here, so that we have an explicit structure that shows how we got to that answer, and then we can explain that structure. So we're still sticking to our original approach. We are using neural models wherever we can, because obviously they perform better on subtasks. But we do believe ultimately the kind of evaluation that we're proposing will not be feasible only with neural end-to-end approaches. That is our claim.
Very interesting. Thank you very much.
Thanks.
Was really a pleasure having you here. If there aren't any more questions, then we'll be going over to the socializing part. It's on Discord again. You all can see the link in our video description. Thanks for attending today. We hope you had fun. We definitely had. And see you again for our next meetup, maybe next time in person again, depending on the situation.